Hello, and welcome to the lecture series on one sample t-tests. So I've discussed how we're going to be going through a lot of different tests now that we've passed the first exam. So here we go. These are called one sample t-tests, what I'm going to cover today, and they refer to, well, t-tests having one sample. They're very similar to one sample z-tests, except now we have more information, meaning the standard deviation of the sample as opposed to the population. So let's get right into it and talk about one sample t-tests. So to start off, when we talked about just one sample tests in general, be it Z or T, but up to this point, we've really learned about Z tests. Keep in mind that we're comparing one sample to a population. So remember, we had our example of, oh, we have 100 vegans, and we measured, you know, they mentioned their diet 15.5 times, these 100 people average mentioning their diet 15.5 times in comparison to the population of overall Americans who mentioned their diet for an average of 14 times and a standard deviation of 6 or whatever. Well, I don't remember the standard deviation for the vegans, or for the vegan example, but we had only the sample average and sample size, and we had the general American population average and standard deviation, mu and sigma. Same thing for the grad students, where we were looking at the overall IQ scores for grad students. 100 grad students was our sample, and we compared it to just the normal healthy population overall. That was our population that we were comparing it to. And remember, when we found z-tests, we were saying, oh, you know, does the population of vegans, we only have a sample of 100, so we want to extrapolate this information to the population of vegans, not just these 100, but all however many millions of vegans there are. We want to see if the population of vegans matches or is similar to the population of the American general public that we have. We want to see if our population of grad students, which we only have a sample of 100 for, if that population of grad students has a similar IQ score to the overall healthy population. We didn't have access to all of the sample data. We only had the mean and the sample size. With t-tests, with one sample t-tests, it's different, but we'll go into that. So, like I said, we had the population variance or standard deviation. If you have one, you have the other. But this is our vegan samples or example. So researchers interested in knowing how often people talk about what they eat. The average person in the American population mentions their diet 14 times, mu, population mean, with a standard deviation of 6. That is sigma, the population standard deviation. The researcher surveys 100 vegans, so there's our sample size, to see if there's a difference between how often they mention their diet in comparison to the American population. The mean for vegans, again, this is talking about our sample mean here, is 15.5. Compute a one sample z-test to decide to retain or reject the null hypothesis with alpha set at 0.05. Okay, so in this example that we had last week when we were talking about vegans and comparing it to the American population, like I said, we have obviously we have the population mean set at 14 for mu, for the average American population. And then we have a sigma, a standard deviation of 6 for the population. And then we only have the sample size and the sample mean in terms of the information we have for the sample. Well, it's a little different for t-tests. So having access to the population standard deviation or variance is not very typical in research. So when we don't have the population standard deviation, but we still have a one sample test, we would use a t-test. You don't have to be scared, sweetie. Okay. My daughter said she was scared, but I'm not sure why. She was just sitting watching her tablet. Everything's fine. I don't know. Anyway, so having access to the standard deviation for the population is not typical. It's not commonplace to have. So when we only have the population mean, but we still have a one sample test, we're going to deal with the t-test. So they're pretty much identical, t and z-tests, except for a z-test, we have the population mean, population standard deviation, and we have the sample size and the sample mean. With t-tests, with one sample t-tests, we have only the population mean. We do not have the population standard deviation. We have the sample size, we have the sample mean, and we have the sample standard deviation. So it's a lot of the same stuff, except you know you're dealing with a one sample t-test if you have the standard deviation for the sample, and you know you have a one sample z-test when you have the standard deviation of a population. So when you're looking at tests moving forward, trying to decide which one is which, if you have one sample, meaning there's only one mention of a sample size, oh, there was one sample of 100 people, blah, 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 and they don't mention another sample, you know you have a one sample test for one, okay. And then look for the standard deviation. If you have the standard deviation for the population, it's a z-test. If you have the standard deviation for a sample, it's a t-test. Okay, so, okay, sorry about that. So we left off saying how the difference between z and t-tests. So now to calculate the t-statistic and the estimated standard error, we have formulas, of course we do. So they're very similar to that of the one sample z-tests because, like I said, they're almost identical tests, except for z-tests, we have more information on the population, meaning we have the population standard deviation. And for a one sample t-test, we have the standard deviation for the sample. So with that, it's all the exact same formulas except the notation is different. So instead of the standard error of the sampling distribution being, you know, the population variance squared divided by the sample size square rooted, or the population variance divided, or excuse me, or the population standard deviation divided by the square root of sample size. Now it is the sample. Now instead of population, we don't have any Greek letters in this, so we know that we're dealing with samples here. So we have the estimated standard error is equal to the square root of the population variance divided by the sample size, or the population standard deviation divided by the square root of the sample size. To find the t-statistic, again, we plug in that estimated standard error in the denominator, just like we did for one sample z-tests. And the top is still taking the mean, the sample mean minus the population mean of mu. That's all the same. It's just the notation is different. So that's why it's important to recognize the difference between a z-test and a t-test, because you'll need to know which one is which moving forward. And again, the easiest way to do that is check that standard deviation. Is it for the population or is it for the sample? Okay, so with us having a new test, a one sample t-test, we have a new distribution. Before we used the z distribution, which was like the standard normal distribution where the mean is equal to 0 and one standard deviation, and the standard deviation was 1, and a z-score of +1 meant that you were 1 standard deviation above the mean. A z-score of -2.5 meant that you were 2.25 standard deviations below the mean, etc. Or did I say 2.5? -2.5, 2.5 standard deviations below. -2.25, 2.25 standard deviations below. I don't remember what I just said, but either way, you understand. So, with the replacement of, now we have our access to the sample variance and the sample standard deviation as opposed to the population, we now use a different distribution. We now have the t distribution. So when we have since we have a distribution using the sample measures of variability, be it variance or standard deviation, we have greater variability in the tails. If you recall, whenever we have the same data set, if we use a data set and calculated the sample variance as opposed to the sample, or the sample variance as opposed to the population variance, the sample variance is always larger because we need to spread out further. We don't know the range of the data since we only have access to the sample. So we kind of tend to spread out just a little further just to make sure we can hug everyone in that sample. So with that being said, the t distribution, which uses sample variance, sample variability, it has a larger variability because it's dealing with the sample. So as an example, God, so many amples. The normal distribution here is this thin black line, and you'll see where it ends on the tails, or at least where it kind of peters out. And then you have the t distribution, and you have that, it's the darker black, it's the thicker black line with two C's. So you have this distribution here for the t distribution, that thick black line, and you see that it actually branches out a little further on the tails than the standard normal distribution. Well, like I said, it's because with sample distributions, t distributions, they have larger variability, so they tend to stretch out a little further. Again, remember, variability is a measure of dispersion, which means just how far the data spreads. So it makes sense that a distribution that is covering samples tends to spread out a little further. Another thing about t distributions is that it's not a one-size-fits-all. Keep in mind that when we talked about the standard normal distribution or the Z distribution, it was like, oh, you know, it's like if every clothing size were standardized and we'd have, you know, one clothing size that fits everybody, or at least one like range of clothing sizes. Obviously a medium's not going to fit every single person, but it had that standard normal clothing size where I can go to any store, and if they have that, I sell the standard normal clothing size, it's good. I know a medium there is the same as any other store that has that same thing. However, with t distributions, each one is different based on the sample size itself. So with Z, we just had the one standard normal distribution and everything converted to it. With t distribution, there's a different one for every single sample size. So it gets a little more iffy. So as we move forward, with t-tests, now we're going to talk, this is just the first of many t-tests that we're going to discuss. But with every t-test, we're going to be dealing with degrees of freedom. Okay? So if you see degrees of freedom in a test, when I'm asking you which test are you using, if you see a mention of degrees of freedom, you know it's going to be some sort of t-test. Okay? So one thing that degrees of freedom kind of covers that. The reason why we use it for t-test is because it kind of covers that difference that we don't have when in regards to information of the population. It kind of gives us that, oh, larger spread, larger data distribution. Oh, okay, we got to find it, you know. So z-test, we have all the information of the population that we want, at least, you know, displayed to us. Z-test or t-tests, we don't. So to calculate the degrees of freedom, you take your sample size minus 1. Now this might sound similar to how we calculated the sample variance. Remember that for population and sample, calculating variance was the exact same until we got to that n. For population, it's just n straight up, population size. But for sample, when we calculated it, it was n minus 1. That same concept kind of comes up here in degrees of freedom. When we calculate degrees of freedom, we take our sample size minus 1. So whatever our sample size is for our t-test, our one sample t-test, if it's 1,000,000, we have our degrees of freedom is 999,999. If it's, you know, a sample size of 100, our degrees of freedom is 99. If it's a sample size of 50, it's 49. If it's 322, it's 321 for the degrees of freedom. It's just taking our sample size and subtracting 1, and that gives us our degrees of freedom. So the larger our sample size, and obviously with that being said, our degrees of freedom, the closer the t distribution is to resembling a normal distribution. So this is like what I was saying when, oh, the larger samples that you have, the more closely you'll be able to anticipate, or not anticipate, the better your estimation of the population is. Mention that, I think, back in the characteristics of the sample mean, where the larger your sample size is, the more accurate your generalizations to the population would be? Well, the larger your sample size is in a t distribution, thus your degrees of freedom as well, the closer it is to resembling that normal distribution that we have for a z-test. So, of course, we have a table. I have published this on Canvas. I made sure to do that before I even started recording this video. But the t-test always use a different table. They're going to use the t table. Now, this is an example of one. The table that you have in Canvas is a little different, but essentially it boils down to this. So in order to find critical values, that's another important aspect as well. The numbers that are in the table for the t-test here, like this 0.741 or this 2.821, the numbers that are in the table proper are not probabilities. You can tell that because it is greater than 1. You know, we have 63.657, that's greater than 1. So where the numbers in the z-tests, when we looked it up, or on the z-table when we looked it up, it was finding us the p-value. For a t-table, the numbers that we're finding here are critical values. So just as a warning, we are not going to be calculating p-values with t-tests. We're only going to use the table and use critical values to determine statistical significance, to determine if we should reject or retain the null hypothesis. But let's get this started. So a couple things you need to know to use the t-table. You need to know your degrees of freedom, which again, like I mentioned earlier, it is just n minus 1. So sample size minus 1. You also need to know if you have a one-tail test or a two-tail test. Now, we've gone over this with z-tests. If your alternative hypothesis is greater than or less than, you have a one-tail test. If your alternative hypothesis is not equal to, it means you have a two-tail test. And this proportion in the tails, be it proportion in one tail or proportion in two tails combined, this number, this 0.5, 0.2, 0.10, 0.05, 0.02, 0.01, that refers to alpha. So that refers to our level of significance. So if we've been dealing with alpha as well, we mentioned it in just previously in this lecture, our previous example from the vegans, our one sample z-test example had alpha equals 0.05, and that's pretty standard. We're going to use that most often in terms of levels of significance. So we have a critical value that is in these tables, and we need to know if we have a one or two tail test. We need to know our alpha, and then we need to know our degrees of freedom. So depending on what our alpha is, that determines what column we need to look in, as well as if we have a one-tail test or a two-tail test. So if we have an alternative hypothesis of not equal to, and our alpha is set at 0.05, this column would be the one we're looking at. Two tails combined down here and 0.05 right there, that's our significance value. This is the table that we're going to be looking into, or the column, excuse me. And then we just need to know our sample size to give us our degrees of freedom to know which row, and then we can pinpoint exactly where we're going. So if we have let's look at this example here. So to find the critical value of t with a sample size of 11 for a two-tailed test with alpha set at 0.05, okay, that's a lot of information that it just gave us. Let's start with degrees of freedom. So our sample size is 11, minus 1 is 10, so our degrees of freedom is 10. So here we go. This is the row we're looking at, this bottom row here. And then we have a two-tailed test, so we know we're looking at these values here, these here. And we have significance level at 0.05. So here we go. We're looking, oops, didn't mean to do that. So we have this column and then the bottom row. So if we want to know the critical values for a one sample t-test with a sample size of 11, and it's a two-tailed test with the significance level at 0.05, the critical values are going to be 2.228. Now that's going to be a positive and negative 2.228 plus minus 2.228, but that is what it's telling us. So the values that we get from t-tables, we're going to compare our t-statistic to them, which we calculate in step 3 of hypothesis testing. But I'm getting ahead of myself. This is the t-table. That's how you read it. That's how you find information from it. And also that's the information that you're getting, critical values from it. Okay. So here's some important differences between Z and T tests. So the obtained value, you have the Z statistic for a Z test, the T statistic for a T test. In the table itself for Z test, you'll get the p-value. You will not get the p-value from a T table. You get the critical values. The distribution that Z tests use is the normal distribution, or the Z distribution if you want to call it that. The distribution that T tests use is the T distribution. The denominator that we divide our test statistic by, for Z tests, it's standard error. For T tests, since we're dealing with samples, it's the estimated standard error. We do know the population variance or standard deviation for Z tests. We do not for T tests. Degrees of freedom does not matter for Z tests, but it does for T tests. And they're both measuring the probability of obtaining a measured sample outcome. So they're both measuring, hey, if our population of vegans is the same as the population for the general American public, how likely is it that we get this 15.5 as the mean? That's what that probability of obtaining a measured sample outcome is. And then as per usual, we're determining whether or not the null hypothesis should be rejected. Okay, so just a quick little thing. So what's the degrees of freedom for the following sample sizes? So 15, 87, 32, 99, 3022. Well, degrees of freedom, again, is n minus 1. So for 15, minus 1 is 14 would be our degrees of freedom. For a sample size of 87, it'd be 86 for the degrees of freedom. For a sample size of 32, 31, 99, 98, and 3022, 3021 for the degrees of freedom. Now the critical value, when we have alpha set at 0.05, now this is kind of practicing reading a t-test, or reading a t-table, excuse me. So we have a sample size of 5 and it's two-tailed, and all of these have a significance of 0.05. So for the sample size being 5, we need to actually, since the t-table itself is using degrees of freedom, we can't use the sample size. We have to get degrees of freedom first. So n minus 1, 5 minus 1 is 4. Now let's just go back up. So we're looking for the degrees of freedom of 4, a two-tailed test with a a significance level of 0.05. The critical values are plus minus 2.776. So that was that one. Degrees of freedom of 5 for a one-tailed test with a significance of 0.05. Well, since it's one tail, we look up here. So this is going to, ooh, I always do that. This is going to be the column that we're looking at. And what was it again? Okay, degrees of freedom of 5. So we have, damn it, boom, this column, degrees of freedom of 5. The critical values for that second example are 2.015, 2015, good year. Lastly, sample size of 8. So before we go to the table, we have to convert that to degrees of freedom. So just n minus 1. 8 minus 1 is 7, and it's a two-tailed test with an alpha set at 0.05. So we know we're going to keep looking in this column, and it was a degrees of freedom of 7. So our critical values are plus minus 2.365. That is the critical values for all of these. And that's how you read a t-table. Okay, so some assumptions for one sample t-tests. First, normality. We assume that the data in the population being sampled, so again, we have the sample standard deviation, sample size, and sample mean. We assume that the population of that sample is going to be normally distributed. We also assume that the data in our sample were obtained through random sampling. I know that's quite an assumption, considering random sampling is not commonly done in statistics or in psychology, but these are assumptions we make. And finally, we assume independence, meaning that each outcome is independent. It's not like one outcome does not influence the other. the population mean that we have does not influence the sample mean that we have, etc. Okay. I hear my children screaming. Lunchtime, crazy. So computing a one sample t-test. So here's an example. So this is an example for one sample t-tests. So Albert et al. Wanted to determine if relatives who care for patients with OCD were as healthy as the general population, meaning did they differ at all? Scores obtained were from a short form health survey, which is a measure of social functioning, ranging from 0 to 100. The mean score for the general population was 77.43. So we know mean score for the general population, that's our population mean. Mean score for the general population, boom, that's the population mean right there. The researchers obtained a sample of 18 relatives. So obtained a sample of 18, instantly we have our sample size right there, n equals 18, who care for OCD patients, and obtained a mean of 62 with a standard deviation of 20.94. So right there, that last sentence gave us all the information for the sample. We have the researchers obtaining a sample of 18, n equals 18, and a mean of 62. So our sample mean is 62, and our sample standard deviation is 20.94. We have the population mean of 77.43, which can be seen through this sentence here, the mean score for the general population. So we have the information we need to go ahead with the one sample t-test. But does the mean score of relatives who care for OCD patients differ significantly from the general population? And boom, there we have it, our significance. So when alpha is set at 0.05. Okay, so it seems like a lot. It seems like a lot of just like, here's an example of a one sample t-test. But let's break it down. Back to the steps. I told you we'd be using these steps throughout. If there's, change might be constant, but for Christ's sakes, these steps are always there. So state the hypothesis, step 1. The null hypothesis is always going to say for one sample t or z test that the population mean for our sample is the same as the population mean that's provided. So the population mean for relatives who care for OCD patients equals 77.43. The two populations are the same, is what the null hypothesis is stating. Now the alternative hypothesis, since we have it mentioned, do they differ at all? Are they significantly different? Didn't mention any direction, didn't say, are relatives who care for OCD patients greater than the general population or less than the general population? It's just, do they differ? They don't really make a direction as to higher or lower. So that gives us an alternative hypothesis of the population mean for relatives who care for OCD patients is not the same as the population mean for the general healthy population. I know I say population a lot, I drive myself crazy, but this is step 1. This is what we walk away with. The null hypothesis is that the population mean of the OCD, the relatives who care for OCD patients is 77.43. And the alternative hypothesis is saying that the population for relatives who care for OCD patients is not the same as the general population in regards to the mean social functioning score. Okay, setting the criteria. Step 2, we got step 1 with our null and alternative hypothesis clearly stated. Step 2, we set the criteria. So we start with alpha equals 0.05. The question has provided that to us. So in this step, we're going to find the critical values. So we knew that our sample size was 18 because the example stated, oh, the researchers obtained a sample of 18 relatives. So for step 2, we need to know, do we have a 1 or 2 tailed test? We need to know our significance level, and we need to know our sample size, because that will give us all the information we need to look at the critical value, to look up the critical values in our T table. So I have a handy dandy T table handy. Yeah, this is the one that's going to be on your, this is the one that's on Canvas. So it's similar. You see up here 1 tail, 2 tails, and then the 1, 0.5, 0.4, 0.3, 0.2, 0.10, it still reads the same. So we had a sample size of 18, meaning that our degrees of freedom is 17. So we're looking, oh, I can't drag it here, but here's 17 in the degrees of freedom column. Now we're looking for, so we have the row that we need, the 17. We also had a two-tail, since our alternative hypothesis is not equal to. So it's a two-tail test, and significance is often set at 0.05. So we're looking for the two-tail 0.05 right here, and then we're going to just go down to 17 at 2.110. That is our critical values for this example problem, where we had a sample size of 18, meaning that our degrees of freedom is 17, and a two-tail test with significance set at 0.05. So again, that means that our critical values are plus minus 2.110. Okay, cool, bitchin', nifty. Moving on. So, two-tail test, plus minus 2.110. So that means that when we calculate our t-statistic in step 3, it's coming, if our t-statistic is greater than positive 2.110, or if we have a negative t-statistic, if it's less than negative 2.110, we will reject the null hypothesis. We will have statistical significance. Okay, now let's get into it. So now we compute the test statistic. So now we're computing the t-statistic. With that, here's the formula again that's been mentioned earlier. So we know that our population mean for the general population that was provided was 77.43. We know that the sample mean was 62. The sample standard deviation, since this is a one sample t-test, so we have the sample standard deviation, that was 20.94, and our sample size was 18. That's all the information we need to calculate our t-statistic here. So let's get it. So it's similar to the z-test and the z-statistic, to where we have to calculate the standard error first, although here it is the estimated standard error. So we take our sample standard deviation of 20.94, ooh, that looked weird, and divide it by the square root of sample size. So I've done that math for you. Once you do that calculation, it equals 4.94. We take the square root of 18 and whatever that turns out to be, 20.94 divided by that number. So the estimated standard error is 4.94. Cool. So that is that part. So now we plug it in to the bottom, and then we just fill in the rest of the blanks. So our sample mean was 62. Our population mean was 77.43. 62 minus 77.43 divided by 4.94 equals negative 3.12. So that is our t-statistic. That is the test statistic that we've calculated from step 3. We walk out of this saying that t equals negative 3.12. Okay. Whew. Now, of course, for step 4, we're going to compare that to our critical values. So step 4, we're going to make a decision. We're determining significance. So here we go. Here we go making a decision. We have our test statistic is less than our critical value. So when it's a negative test statistic, we want it to be less than that negative value. So keep in mind that our critical values were plus minus 2.110, and we had a test statistic, a t-statistic of negative 3.12. So we're going to be saying, oh, we want negative 3.12 to be less than our critical value of negative 2.110 to have statistical significance, to reject the null hypothesis. And oh, hey, what do you know? It is. Negative 3.12 is less than negative 2.110. So we're going to reject the null hypothesis. So that's essentially saying, hey, the social function, the population of relatives who care for OCD patients is not the same. Their mean social functioning is not the same as the mean social social functioning of the general. Oh my God. Excuse me again. It's not the same as the social functioning for the general healthy population. So, boom, we have statistical significance. These two populations are not equal. Hence, our alternative hypothesis saying that the mean, or the population mean, does not equal 77.43. So we have Cohen's d. Very similar, except again, since we're doing a one sample t-test, instead of having the population standard deviation, we have the sample, but it's still pretty much the same concept. We're taking our sample mean minus our population mean, divided by the, in this case, the sample standard deviation, and that gives us a negative 0.74 for Cohen's d. So is this a weak relationship, a medium relationship, or a strong relationship at negative 0.74? That is technically a medium effect size. That's a medium strength Cohen's d because it is between 0.2 and 0.8. Doesn't matter that it's negative. It's not weak because it's less than 0.2. Keep in mind, we're only looking at the number. Ignore the negative outside of my facial parentheses here. We're only looking at the number itself. My face is 74, so that is what we're looking at. I'm gonna stop hitting myself. But, so we have negative 0.74, that it would be characterized as a medium strength Cohen's d. It's almost strong because it's almost at 0.8, but according to the guidelines that we have in the class that we have been working with, we have a medium strength Cohen's d. Okay, so now we're just going to look at these. I want you guys to determine the difference, to look at these and determine, are we dealing with a z-test or a t-test? So we have, I'm going to read all these, then you can pause it after I'm done reading, so then you guys can kind of work them out on your own, and then I'll go over the answers. Okay, so this first bullet point, population mean 5.72, population standard deviation 1.32, sample mean is 4 and sample size is 45, so that's the first one. Second one, sample mean is 12, sample standard deviation is 2.5, population mean is 13 and the degrees of freedom is 20. Third example, comparing the stress of 100 college students with a mean of 4.2 and a standard deviation of 1 to the general population with a mean of 4. And lastly, do high school students order more frappuccinos per week with a mean of 2 and a sample size of 50 than the general population, mean of 1.5, standard deviation of 0.5? Okay, so go ahead and pause your video now. Okay, I just want to leave a stupid face for you guys to see. Anyway, so now I'm going to go over them. So for this first example, again, how do we characterize the difference between Z and T tests? Well, a quick way, since both of these only have one sample, we're just differentiating between Z and T. Quick way is to look at the standard deviation. Which one do we have? So that first one that starts with the population mean of 5.72, that first bullet point we have, where's the standard deviation? Okay, so we have a sigma of 1.32. That is the notation we use for the population standard deviation. So, boom, we can stop right there. We have the population standard deviation, so this would be a one sample Z test. Z has Z population. Anyway, next one, sample mean of 12, sample standard deviation of 2.5, boom. We, again, looking at that standard deviation, we have the sample standard deviation of 2.5, so we can say that would be a one sample t-test. We can also go a little further and see, oh, the degrees of freedom is 20. Now keep in mind, we only use degrees of freedom for t-tests. And in this example, you know, we're only comparing Z and T, so when you see a degrees of freedom, you know it's going to be a t-test. As we move further in the class, we'll have more differentiation between the different types of t-tests. But for now, comparing Z versus T, you see degrees of freedom, we know it's a t-test. Okay, now the next one, a little more wordy, as opposed to just pooping out the answers to you, or at least the, you know, the information. Now we kind of have to read and ascertain some information. So comparing stress of 100 college students, boom, you've given me a number of college students. So I'm gonna say that's my sample right there. You're gonna give me a number of people that you have some information for, that's gonna be your sample. With a mean of 4.2 and a standard deviation of 1 to the general population mean of 4. Okay, so we have our sample size of 100. We have our sample mean of 4.2. I know that's the sample mean because it says comparing stress of 100 college students, and immediately after in parentheses, it says mean and standard deviation of 4.2 and 1 respectively. So I'm gonna assume that's going with those 100 college students that they just mentioned. So we have the sample standard deviation of 1. So hey, that looks like it's gonna be a t-test, y'all. And then look at the general population, we only have the mean for it. So we have a 1 sample t-test for this comparing the stress of 100 college students. Excuse me. Last one, do high school students order more Frappuccinos per week, mean of 2, sample size of 50, than the general population, mean of 1.5, standard deviation of 0.5. Okay, so high school students with a sample size of 50. We know that our sample here is high school students, and the number of high school students that were sampled was 50, and they have a mean of 2. So they order 2 Frappuccinos per week. The average of these 50 students said they order 2. Then the general population, mean of 1.5, standard deviation of 0.5. Okay, so we have the population mean and standard deviation, and we have the sample size and mean. Again, look for that standard deviation when we're comparing Z and T tests. We have the population mean of 0.5. We do not have the sample standard, or excuse me, I said population mean. I meant population standard deviation. We do not have the sample standard deviation. We only have the sample mean and the sample size. So when we're comparing Z or T, this last one is going to be a 1 sample Z test because we have the population standard deviation. Okay, so that concludes our lecture, our first lecture on 1 sample T tests. Next lecture, I'm going to go over confidence intervals. But I thought let's kind of keep it small. Let's focus on one thing. So here we've gone through the steps 1, 2, 3, 4, state the hypotheses, set the criteria, calculate the test statistic, and then making the decision. So we've gone through that for a 1 sample T test. We've gone through that for 1 sample Z test as well, but now, hey, it's a different test. We've gone through how the differences between Z and T tests. There's more variability with a T test because we're dealing with samples. And samples always have larger measures of variability because we kind of have to guess. We have to guesstimate how far the data is going to spread of the population. And with a T test, with a sample, we don't have the whole population, it's just a sample. So those T distributions are longer. They tend to be further, they branch out a little further, just like the standard deviation or just like the variability of samples do in comparison to a population. We've also discussed how to read a T table, different than reading a Z table. And we also know that in T tables, we do not have probability. We're not finding p-values in a T table like we do for a Z table, but instead the numbers that spit out at us in a T table is going to be critical values. So we're not going to calculate p-value for T tests. We're just going to use critical values and compare it to our test statistic, our T statistic. Keep in mind that it's a plus and minus critical value, where if our T statistic is positive, we want it to be greater than the critical value, greater than the positive critical value. And if our T statistic is negative, we need that to be less than the negative critical value. As per usual, if you have any questions, you know when my office hours are. I'll be there, guaranteed, waiting for people. If you want clarification or just have questions or want to clarify your own head or your own peace of mind, feel free to stop by at any time. I'm there until the end of them. So that's all I got for you. That's 1 sample T test. So as per usual, like and subscribe.